Thank you all for joining this panel discussion. So, we'll jump right in. We have a pretty good cross-section of panelists out here. The title is the GPU, how do we disrupt GPUs, or do we disrupt? Are we always going to live with GPUs? And really, the question we want to ask is, can smart memory and smart storage actually be this disruption and democratize access to AI beyond the GPU, or maybe introduce some new paradigms with the GPU itself? So let me briefly introduce the panel. So we have JM, he's a CEO of Farm GPU. He's the guy buying the GPUs and storage and memories, so he's going to pay all our bills. And then we have, and then of course he's an innovator from storage, and then now on the GPU frontier as well, NeoCloud, as we like to call the GPU-only exclusive cloud providers. And JM is running a 7 megawatt data center out of Sacramento, so not too far from here. If you're concerned about all the earthquake zones, bring your data over to Sacramento. We have Nilesh Garia, so we have two Nileshes on the panel, but Nilesh is CTO of Numem, which is actually an innovator in the MRAM space and alternative memories, because it's all about the memory wall, so developing these humongous chiplets as an alternative or as augmentation to HBM memory. And of course, we have Stephen Bates from AMD, fellow and driving a ton of innovation in the storage, memory, compute space. So it'll be interesting to hear some thoughts from Stephen. And then of course we have Jungmin from SK Hynix, and he's leading all of their processing in memory research and pretty much all the groundbreaking stuff that's coming out of the memory forest team. Is that the right team? So pretty cool name. I'd like to live in a forest as well. And then finally, Vikas is a VP and GM at MaxLinear. So they're driving all the storage, accelerators, compression, encryption, a long list of innovative products out there in the market. And I'm Nilesh Shah with 0 Point Technologies. We do compression IP for memory, for storage, cache line compression. So you might hear if you hear a lot of talk about compression, just call us out, because there's a bit of a bias out here on the panel, but we'll try not to make it all about compression and talk about other innovations. So maybe if any of the panelists want to give a brief intro about yourself, if I didn't do justice, now is the time.
You did justice. Yeah.
I did justice. Fantastic. So maybe just a quick show in the audience. How many people out here care about GPUs? Okay, we have a few. How about storage? Okay, mostly storage. Any memory and that that thing called CXL. Okay, we have a few. And how about HBM memory? Oh, HBM. Okay, a few. And anyone on the alternative, what I like to call the neo chip side, so accelerators besides the GPU for inference specifically? Any representation out here? Maybe not. Maybe one. Nilesh out here on the panel. All right, so let's jump right in. I have a few questions, and what I'd like to do is, we have about 40 minutes or so. I'd like to have maybe 20 minutes. I prepared some questions, but then I'd like to open it up to the audience out here to actually ask some questions. So let's jump right in, right? And maybe I'll direct this question to all of the panelists. Where is the real choke point when it comes to AI inference? I'll be more specific. AI inference, right? So is it compute? Is it memory? Is it storage? Is it something else? And yeah, what is there a problem to be solved? Anyone on the panel? Stephen, yeah.
Hi, everybody. So if we're talking about inference in particular, I mean, at the end of the day, AI is just a lot of math, right? So we do a lot of basically vector multiplication and things like that. GPUs are really pretty efficient at doing vector math, which is why people tend to use them. But obviously, you can do another chip that is even better or more efficient than doing that. And I think we're seeing that, right? All the hyperscalers have, projects internally trying to build chips, typically on the inference side, because that's, I think, where there is potential to have benefit. But I think one of the challenges that everybody's facing is that these large AI systems are very much systems and they're not individual chips. So, you've seen NVIDIA move to building larger and larger things, like at the rack level. AMD made some announcements recently on our rack scale architecture. So it isn't really enough to have like a chip, right? It's like, how do you move the data so that it's where it needs to be, when it needs to be there, and have that happen efficiently, effectively, and reliably, like over and over again across fleets of hundreds of thousands of whatever these devices are. So for me, AI inference is as much a data movement problem as it is a data processing problem. And I'm very much focused on the data movement side. And that's where I think this panel is interesting, because we can talk a little about how do we get the data where it needs to be, when it needs to be there, in the format it needs to be in, so that whatever chip is there can do the math in the most efficient way possible.
Got it, thanks. Any other thoughts? Joe?
Yes. So from our profiling on H200 GPU with latest VLLM models like the Llama 3.1 and 4, definitely we could see some utilization mismatch. So in compute intensive prepare phase, we can see the GPU utilization is above 90%. But the HBM utilization is 30 to 40%. But on the other hand, the memory-intensive decode phase, the GPU utilization drops under 40%, but the HBM utilization goes up to 90%. So I think this nature of LLM inference makes it is very hard to maximize the utilization of in homogeneous GPU system. So maybe we can discuss again this more detail in this panel talk. But I believe that so we should move forward to the heterogeneous AI system, including memory and storage solutions. So and also NVIDIA announced the Rubin architecture, right, at AI Infra Summit last week maybe. So it can be see the part of this trend. So yeah, that's my opinion.
Okay.
Yeah, we should figure out more the smarter architecture or heterogeneous.
Got it. You might want to come a little bit closer to the mic.
Okay.
But yeah, essentially your point is more efficient architecture, so we're not underutilizing these expensive devices. Any other thoughts, or Jim, go ahead.
Yeah, there's a big difference between doing something where you're doing research development, like small scale systems with a few GPUs, or doing inference on a single model, and you're just looking at like small batch size, low latency stuff, versus inference distributing at scale, something like where OpenAI and Anthropic are at a point where they're actually making actual real revenue on these platforms. And so that is where, like you just mentioned, the NVIDIA Rubin CPX announcement that was at AI Infra last week that sort of caught everybody off guard. When they announced Dynamo, it was, hey, there's this prefill phase that's compute bound, and then the decode phase that's memory bandwidth bound, and then we have this distributed inference engine to basically use the best chips for doing that. And then it shouldn't be that shocking that NVIDIA comes out and says, oh yeah, now we have this thing that turns out to be really, really cost optimized for this first phase in prefill, utilizing PCIe Gen 6 as the interconnect instead of NVLink, utilizing GDDR7 instead of HBM, looking at that whole stack. And if you guys saw the announcement, 20 petaflops of FP4 compute per chip is pretty wild compared to the systems we have today. So, but there's still a lot of development going on. Like most of the people that rent our compute are renting like one system at a time, fine-tuning a model, or like serving an inference endpoint for some customer to test in some enterprise use case. They are not like hitting this thing with 20,000 batches. Like it's like very low requests and small stuff. So you have both ends of the spectrum. There's still going to be a bunch of development going on, like what people need to do to make the models work. And then Then there's let's solve this future problem where inference is happening at scale, which are two very different things.
No, thanks. And by the way, I start off the discussion focusing on AI inference, but maybe a question for JM again is, is training done? Like, so there's maybe 5 companies in the world that can do training, and then the rest of us just focus on inference. Where do you see like the demand? And like for this audience, right, that's doing storage and stuff, should they even care about training, or let the folks that are deploying do their thing?
Yeah, one of the things that we had some customer training a custom version of DeepSeek on our platform like last week, and I was looking at the checkpointing bandwidth and trying to measure some stuff to figure out kind of what they're doing. And but for the most part, it is the large hyperscalers doing these large training runs, and I think that the GPT 4.5 and GPT 5 level models that we're seeing are like the 100,000 type GPUs clusters. And then now Elon's moved to 200,000 GPU clusters. Okay, to get a 10x of that, 1 million to 2 million GPUs, that's a lot of GPUs. Nobody's ever built a data center that big. Yeah, there's not gonna be that many people doing these mega training runs. There's only enough people, there's only a handful of companies you can count on one hand that have the capital and CapEx to go build those out. But that doesn't mean that all the other training use cases for storage, for instance, like trying to understand how to do efficient checkpointing and parallel file systems for good bandwidth during training, or the KVCache offload, some of the stuff on inference. It doesn't mean that none of that is important just because a handful of people are doing it. I think it's all still really important.
Okay.
Yeah.
And by the way, coming back to my question, where is the choke point? I think, Stephen, you said it's really moving the data to where it needs to be. So maybe I'll ask the question to address this. You have storage, you have memory, and maybe Nilesh, I'll point this question at you. We're seeing a lot of talk about chiplets and UCIe, and there's CXL out there to try and fill in like the memory hierarchy. So really, I mean, what's going on with this movement that Stephen was talking about, and what are you doing about it, right? And what should this audience be doing about it? What actions can be taken to remove this choke point?
Good question, Nilesh. So I think since last few years, we have seen like with the HBM, all DRAM-centric solutions. And as all the folks kind of talked about, the heterogeneous system is coming into play. You'll see like in next 5 years, with the advancement in the foundry technologies, starting we have like MRAM and RM, which have kind of different characteristics. The way to enable those different features with the different retention times in MRAM and with the KVCache, that will kind of come into a big play. The reason is the standby power, it goes with a 0 standby power, right? So if somehow we can orchestrate with the software, then you can kind of leverage that capability.
Got it. And maybe I'll direct this to Vikas. You want to add to that?
Yeah, several thoughts, and I'll just put it out there. So I think we are at an interesting time where things are moving from just compute to a holistic understanding of what the system should look like. So all the way from, for sure, there are GPUs, but the different tiers of memory and how data is getting shaped as well as moved across the different tiers of whether that be CPU, GPU, or different memory layers, and then finally application layer on the top. So interesting time in the sense that there is an opportunity to innovate actually across the layer and optimize systems, specifically with respect to the power consumption that we are looking at right now. I think as Steve talks about this, for every, let's say, a picojoule of compute, there's probably roughly 10 picojoules. He hasn't done the math, but thereabouts, right? A significant amount of actually data movement has to happen for a picojoule of compute to happen. Specifically, what we should look at is KVCache offload, where for, especially in the context of inference, for every, let's say, if you take a 128K head, you will get 40 gigabytes of memory. And then if you keep adding to it, especially as the transformer models have longer context length or attention span, this bloats through. And I think you were talking about the CPU or GPU utilization, which is well below of what HBM is able to cater to. So I think that entire concept has to evolve to account for KV-cache, tiering of KV-caches, data acceleration, especially or compression and decompression and other kind of data services, whether you do that as an inline or an offload. So the accelerator cards are becoming extremely important in this entire architecture.
Got it. Thanks. The other thing I was going to say is we talk about memory and storage as if they are equally important. So maybe, Jungmin, I'll direct this to you. I mean, where do you see like storage, and is it always going to be HBM dominating the AI inference, or as Vikas was saying, there are innovations with smart storage technologies like compression, or I don't know what else. There might be some other innovations. But can smart storage and smart memory, right, that's kind of part of the title of this panel, make a difference, right? At least on this panel, we have Nilesh, you're doing some MRAM, but you're doing smart MRAM. You have some controller technology. Jungmin, you're looking at processing in memory, right? Because you're doing these accelerators. And Stephen, you come from a long background on computational storage. But do any of these innovations, does any of them have the potential to meaningfully move the needle? And as an industry, do you see everyone looking at something different than just building SSDs with the usual controller, PCI Gen 6 and do Gen 7 and Gen 8 until like infinity, right? Or is there some innovation to be done?
Yeah, so first of all, in HBM perspective, so if we look into, for example, bandwidth, so as the context lengths still getting longer, it means that the attention operation demands more memory. And then, the latency, the execution time is largely dominated by the bandwidth. So in that perspective, I think the bandwidth is still continue to increase. And this also make the capacity more critical because the increased KV-cache has to be stored. So I believe that for example, the GPU scaling is continue to increase, but just enough to meet this minimum requirement. But at the same time, we can also see the effort of KV-cache offloading from HBM to second-tier memory, for example, the DRAM, CXL memory, and SSD, or Numem, for example. So, and my research group also, not my team, but the other team in our research group also focus on the CXL disaggregated memory. They working on connecting CXL disaggregated memory to multiple GPU system to address this kind of issue. For example, the mitigate the network overhead between multiple GPU or sharing the KV-cache. And also my team also focus on the PIM architecture Nilesh also mentioned. PIMs, the PIM is, get some system benefit. It means that it can maximize some memory bandwidth in the device level. So there are so many industry approaches and some new architectures. So so that's my point. And I believe that this kind of disaggregated memory system architecture or some heterogeneous memory or some smarter tiering solution will become more advanced. So, yeah.
Okay, any other thoughts from anyone else? On is there a play for smart memory or smart technology, and is it like needle moving, or is it like maybe you'll influence 0.1% of the market?
So I think a lot of these innovations will have to coexist. But sitting in the panel over here, I can tell you that if there's a fundamental movement, significant needle movement that can happen, is which is from transistor level up, is fundamental technologies like what Numem is doing. If they can come up with an equivalent of DRAMs one of these days, that would be a fundamental shift. But otherwise, a lot of these innovations will have to coexist to collectively move the needle. That's my opinion.
Any other thoughts?
I'm going to mention the C word, compression. So like large scale inference, right? Especially if we have like, John Michael can talk, he sees this all the time, right? We're going to have a lot of users asking a lot of questions across a lot of models all at the same time, and we're trying to service that on a compute farm. Like for me, that just sounds like data movement up the wazoo, like just crazy. And so it's not even really for me about on-disk storage. I'm not really trying to save dollars per gigabyte of capacity for storage. This is really about data in flight, right? If I've got to move data all the effing time, like if I'm literally moving data all the time, moving models around, moving context around, moving users' responses around, I want to move less bits. And compression just makes an awful lot of sense to me in that regard. And whether it's done, to the side with something like a MaxLinear Panther, whether it's done inline, in an RDMA NIC or a DPU, that's kind of second order. Did the GPUs, start having compression offload engines in them? I'm more decompression, right? I'm thinking like we're compressing and then we're moving and then we're decompressing so we can do operations. If we can do operations on compressed data rather than decompressing the data, like linear algebra on compressed data is possible, right? It's possible in the same way that homomorphic encryption is possible. So does that make any sense to have accelerators that can do linear algebra on compressed data if it's compressed with LZ4? Potentially, right? So, that for me is the low-hanging fruit. The ability to save picojoules per bit by moving less bits around using compression. And it doesn't even need to be lossless, right? AI is fuzzy, so lossy compression is another possibility, and often that gives us much better compression ratios.
Interesting. Nilesh, I know you wanted to say something, and JM, I know you were about to say something.
A quick one. So I think where we'll see in the future is, say, 8 parts of DRAM versus 1 part of MRAM, right? That will be like a starting point in the data server kind of AI memory, and then eventually you will see processing capability influxed in those MRAM or any other new type of memory for the data saving, for the power savings.
Okay. JM, go ahead. You were about to say something.
Yeah, it's amazing to see people rediscover the memory and storage hierarchy in the pyramid. They're like, maybe we shouldn't put everything in HBM. It's $20 to $30 a gigabyte. And there's this thing that's 100 times cheaper. We should probably figure out how to use it. And people also discovering that flash is pretty high bandwidth, and there's a lot of interesting things you can do. I know we just came from the PLIAPS talk next door about the KVCache offload, and I know I think we have a question about that here on the panel here. But
No, go for it, yeah.
Yeah, this is, when we're thinking about some of the use cases for storage in inference, KVCache offload and RAG are the only two really ones that are out there that are emerging. But the KVCache one is very interesting, where it's when I had Gemini kind of look through some of the models to get me some idea of some of the users and context size. But if you have a FP16 with a Llama 370B, and 200 users at just 128K full context, it would be 8 terabytes of KVCache. And so, you're not going to store that in HBM. That just doesn't make any sense, especially when these long context windows. I'm sitting there on with 10 different windows open every day. I've got Claude and ChatGPT and Gemini and Cursor open, and I'm going back and forth and waiting 5 minutes, bouncing on this other thing here. There's all these long context conversations. It doesn't make sense at all to keep that in HBM for the entire time. So one of the metrics that people are benchmarking for KVCache offload is time to first token, but that's not the value. The TCO value comes from be able to run a higher batch size and more users on the HBM. So that is where it's the dollar per million tokens that you get from running a higher batch size on inference. It's not like the time to first token is like a side effect. It's nice to have, but you can already have a very fast time to first token by going parallel on the prefill phase. I just shot ChatGPT 5 like a 40-page PDF and it responded within half a second today. That was not anything that had cached. It just parallelize the prefill phase on a bunch of GPUs. So yeah, the value is not time to first token. The value is in TCO reduction, running more users on the GPU, getting more more tokens. It's exactly like SSDs work with higher queue depth, block size. It's like almost exactly the same.
Got it. All right, no, thanks. So maybe what I'd like to do is switch to the audience. Let's get a few audience questions, and then we can come back to some other regularly scheduled questions. Maybe, Jim, if I can grab your mic. Yeah, go ahead. There's a question out here. All right, go ahead, John.
I'm curious.
I think it's on. Yeah.
Is it on?
Yeah. No?
I don't think so.
Oh,
Now it's on.
yeah.
Okay, so does confidential computing play into this for the large models, or is that just orthogonal?
Anyone want to take it?
Confidential computing is a huge part of this, John. Yeah. So, I mean, I was talking to a very large customer of ours the other day, and they were like, so if I run you in like an untrusted environment and VMA uses part of your GPU at the same time VMB, there's no like cross pollution possible, is there? And I cried and I said, it's time for the weekend, and I went for a beer. Yeah, so, I mean, there's a huge challenge here around how do we keep data confidential, not just on disk, but at the points of compute. AMD's done amazing work with like locking down on the Zen architecture on the CPU side, and a lot of that is starting to appear on the accelerator side as well, right? We do want to be able to share these accelerators in virtual environments. I don't know if anyone's like looking at SIOV, but that's an area that I'm very interested in as we think about, well, how do we share a GPU across a bunch of different tenants, essentially.
Ordering of compression
Yeah.
and encryption kind of matters.
Yeah. So getting these things right is really, really important, and doing all of that. And there's a bunch of work happening in that space, but there's more to be done for sure.
Jim, you had some thoughts?
Yeah, and it was exciting to see on the latest AMD CPUs, they support TDISP. And it's like, great, does anybody have a drive that supports that? Okay, we're not there yet. Okay, so
have to write spec
this,
for that,
this whole
apparently.
confidential computing stack, I know it. Nobody's done it full end-to-end yet, as, obviously the drives that support this link encryption and stuff are just coming out. But, I think Microsoft claimed to have an H100 instance that they had, with the full confidential computing stack. But at the time, it's just like the memory encryption from SEV and other stuff. So people were trying to, we had a customer requesting it, and we wanted to test some of the Supermicro on our H100 box. So I sent them an email like, hey, I want to upgrade the vBIOS on our H100 so to support confidential computing. They were like, yeah, don't do that. like wait, I shouldn't update the firmware on the GPUs. They're like, no, there's a chance that they'll brick. Do not update them unless you absolutely have to. So it's sort of where it's like, oh gosh. But no, there are customers that are like trying to think about, that would appreciate this end to end, and it's very important.
No, thanks. There's a question from Bill? Yeah, go ahead, Bill.
I'm Bill Gervasi from Monolithic Power Systems. And one of my criticisms of us as an industry is our speculation doesn't seem to have a very high hit rate. When I look at the efficiency of a data center measured by data operated on versus data moved, it's so close to zero that it's embarrassing. What do you guys have in mind for how we could increase our hit rates and reduce the amount of speculative access that is never used?
I can take it. So,
Yeah, go ahead.
yeah, basically at Numem, so we have developed a controller basically with a prefetch mechanism, right? So that needs to be well integrated in the whole system to get you a good hit rate scenario, right? At the heterogeneous level, not just at one particular memory subsystem, but at the heterogeneous level. It needs to have a good prefetch system.
So how does that increase the hit rate of speculation? You know where I'm coming from on that. It's that you look at, say, a typical 4 kilobyte transfer from an SSD into main memory. and then 100 bytes of that are actually used because a majority of it is just updating pointers. It's not actually using the data that's in that 4 kilobyte cache. DRAM, it takes 10 kilobytes of activation to fill a 64 byte cache line. Your data efficiency is like 0.25%. So 99.75% of that access was completely wasted. How can we increase the amount of data actually used versus what's accessed?
I'm going to push back on that and say GPUs are much, 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 much better than CPUs for that. So when we do a DMA into HBM, especially for AI, I can pretty much guarantee everything we DMA into HBM is going to be operated on computationally because it's part of the vectors of the model of the parameter. And then when we do math inside our compute units, we have very wide registers, and we basically do A times B across the elements in a vector a very long way. So I think if you actually look at, and we don't do branch prediction in GPUs, maybe we should, but we don't. So it actually ends up that pretty much everything that gets DMA'd into HBM will get used, and we tend to be quite efficient in terms of like the math that we do on that particular data. I agree CPUs are way, way worse at that, and maybe that's one of the reasons why they're not so good for AI. But GPUs follow a slightly different model. So I'm going to push back on you a little bit there.
Any other questions? Yeah, go ahead. Bill?
So a number of you have talked about how you want to reduce data movement in a variety of ways, including compressing your data before you send it. However, why are we not looking more carefully at compute near data, whether that data is in memory or in storage? We have protocols, and they may be specific right now to specific GPUs, but we should be able to take those protocols and implement them to compute near storage, compute near data. And I'm interested, I hear a lot about, well, we can do all of this in the GPU. What is the major hurdle to do compute near data instead of moving it at all?
Any takers? I mean, if Stephen is going to encrypt all the data before it goes, you're screwed, right? So there's nothing left. Yeah.
Fully homomorphic encryption is the thing. And GPUs can do it quite well. No. So it's an interesting point, and one of the things I've been talking to storage vendors about is RAG, right, which is something we haven't touched on much on this panel. But, RAG and that ability to bring, local data in to answer inference is pretty interesting. But it means you've got to be like vectorizing, or the word, I think I've made this up, ragification of data is something that, the storage systems could potentially do, because you don't necessarily need to throw the latest and greatest GPUs at it. But I think something people often don't realize is when GPUs do AI, they don't do it on your unstructured data, right? They do it on embeddings or vectors that are generated based on models of that data. So the GPUs never see the PDF, they never see the video, they never see the whatever, they see a bunch of vectors that represent that data in a highly dimensional space. And so for me, that is an area where storage could really help, in the sense that if storage vendors were able to do some of this embedding ragification, for want of a better word, that would be super, super useful. John Michael, I'd love you to chime in on that if you.
Yeah, just on the RAG use case, if you go do some of the vector database bench we did Milvis is one of the vendors that has this database benchmark where for 100 gigabytes of embedding data, on the CPU, it took like 36 hours to do the embedding. You're like, no wonder people are charging like thousands of dollars per terabyte to per month to do vector database stuff. But yeah, it's so there are optimizations that, we talk about, like if And I know some of the ISVs that are selling storage boxes have been talking about this. Like, why don't we just vectorize everything that's coming in, because we know we want it to be searchable by an LLM at some point. So it makes sense that. And then there's a question of like, how much does that grow the amount of data being stored, because now you're storing more stuff with vectors every time you store data. But yeah, it totally makes sense.
Yeah, I know.
Yay, more storage. Yeah.
Oh, Bill has a question. Yeah, go ahead. And I think we have maybe 10 more minutes left.
So
we'll.
the third bill. I want to push back a little bit on John Michael's statement about there's only going to be a handful of large companies that do training and everybody else is going to do inferencing, because I think that's unrealistic. I agree there are going to be a handful of these gargantuan models, but everybody and his brother is going to be training models, specific models, smaller models that do other things. But the thing I wanted to ask about is, you guys brought up RAG as a way of, is like Curtis pointed out this morning, as soon as you train a model, it's now obsolete because data keeps evolving. Plus the fact that most companies don't want to commit their data to a large language model because then it essentially becomes public. So you use RAG as a way of doing that. But RAG's actually very inefficient, because now what you're doing is just throwing a much longer prompt at the thing to give it a whole bunch of contextual data. So my question is there a way that you can break up the training sequence in such a way that you can have a foundational model and then constantly retrain with proprietary data that you keep internal?
Yeah, I mean, the answer is yes. That's fine tuning, right? So you can do that, yeah. And I think it'll be interesting to see where RAG makes a play, where you don't change the model parameters, but you have this contextual data that you can bring into the inferencing, versus fine tuning, where you take a foundational model and you actually tune the parameters with new data so that your foundational model becomes specific for you. Yeah, there's two different ways. You can even blend the two, where you're like, some of the data I'm going to use for fine. And I don't, I defer to people like John Michael who are seeing what actual people are actually doing on real systems, because I don't really see which is more popular right now.
Go ahead.
Yeah. The differentiation between the fine tuning and the foundational model training thing. I think there's going to be a bunch of value in having this data one way or another, right? In figuring out how to make use of it with the models. One of the interesting bits, we were talking to one of the storage ISVs where they're like, our customer, the requirement is like 10 terabytes a second of shared bandwidth. There's no number of nodes, no capacity in terabytes, or no cost. No, that's the requirement is 10 terabytes a second, right? So there's a handful of customers like that are like, just build as much as possible and as fast as possible and just go crazy. And then there's the real world, which everybody else lives in, which we have to cost optimize stuff and look at TCO and look at performance. And I'm thinking about this a lot in the checkpointing context, right? There's every single company seems to have some different special sauce of how they do it. And if you're AWS and have millions of hard drives on S3, well then maybe that's a good strategy for you. But not everybody else has a data center with millions of hard drives.
Actually, that's a good point. So maybe I had one question I wanted to follow up on the TCO, right? Where people are spending money. So, John Michael, since you're buying all this stuff GPUs and storage and maybe accelerators from the likes of MaxLinear, I mean, do you see the economics flip? Is it the majority of the money will always go for GPU purchase, or can anyone do something smart? Can MaxLinear do something with whatever their cards, or Numem comes up with some MRAM-based HBM, or Jungmin does something like custom HBM, right? Is it going to change anything from how you see? What are you going to buy in the next 5 years? Is it 90% of the money is going to GPUs and everything else is Like, you know.
Yeah, so one way to look at it is just from the BOM, like the people are doing deconstructing some of the, you know, the GB300 BOMs and looking at like how much HBM is on there and looking at, oh wow, this on a Blackwell, like half the cost is HBM. Holy moly. But the other way, like just from Nilesh's point on the TCO, like how a customer or a data center or a neocloud thinks about this is like, I'm going to buy something, how much money is that going to return? And if we can make a profitable storage business and you buy storage and say, I could sell it for this much, that's great, you have that recipe. For GPUs, there's a very large market for NVIDIA GPUs. So we know when we buy something that somebody's customers are making 3-year commits for, I will give you this dollar per hour for every GPU, you know, for 3 years. Okay, great, you handshake and you go along your merry way. Well, obviously we're gonna spend most of the money on the GPUs because that's what's driving. But when you buy that many GPUs, well, 20% of that data center cost is now networking. So trying to figure out, okay, well, how do you get that cost down? Storage costs, they're like trying to squeeze everything else because they're like, well, the customer's paying for the GPUs, so let's just reduce everything else as like low as we possibly can. But that's how we're actually thinking about it. And I know that's not exactly right. There's lots of other ways to make money besides just selling the GPUs, but that's that next step, right? Which is how do we get all that data away from AWS? Get back to us.
I mean, one of the things that has to drive that behavior is the total power consumption, right, as part of the TCO. So for sure there's as a BOM element in terms of the dollar, but there are intangible elements which eventually convert to real dollars is the power consumption itself. And I think that consideration has to start coming into picture before people make their purchases. So for example, from, we just wrote out a TCO paper on what we call performance-based TCO using accelerators. And therein we demonstrate that the impact of power consumption is more than 10x if you use, for example, compression, decompression along the pathways. So those considerations have to be taken going forward.
Got it. Maybe, good, gentlemen, you want to have a comment?
Yeah, I agree with the opinions, and then I also believe that GPU will remain as a dominant in somewhere, but the end scaling GPU is not a sustainable way. So due to you already mentioned the huge power and energy consumption. So there are some industrial approach, for example, some low power solution like embedding analog memory computing directly into the base die of HBM. So that can be bring a huge cost. I mean, the power saving in AI system in these days. So I believe that kind of custom solution is to become truly feasible in the near future. So that's my opinion.
Got it. Stephen, you have a comment on that?
Oh, I always have a comment. I think that one of the challenges is even if somebody comes up with like a really good accelerator chip, you need software. And I think one of the interesting things is I think AMD actually have like a pretty good portfolio of silicon right now, and we have a good shot at like continuing to eat into NVIDIA's market share. But it's where we have to invest is software. And when I look at a startup that's like talking about, we're going to have the best AI chip, it's going to be, 20% more efficient than someone else. I'm like, dude, like, you have to go write like 1 trillion lines of code and have that code run in production for like 1 trillion hours. And then maybe you've got something that, a hyperscaler is going to take a look at. And I think that's something that we keep having to come back to. And that's always been one of my challenges with processing and memory. We've never had a good software model for it, right? Caches are a thing. Like even on the GPUs, we have multiple levels of cache. So processing in memory means we have to evict caches because we can't have the data in cache. It's got to be in the HBM or in the whatever. And at that point, we've already lost the race because those evictions take a bunch of time. So that, I totally love processing in memory, but it's the software model that really I struggle with there. And it's the same for a lot of the other things. Like software is just such a key part to all of this. And that's why NVIDIA have 95% market share right now, right? Because they made the investments early and they continue to do that. And fair play to them for doing that.
Got it. And if that's true, right, if your statement is true, and let's say Jensen called you up, right, Nilesh, tomorrow and said, hey, make your pitch to me, MRAM-based chiplets, let's get rid of this HBM. What's your pitch? I mean, will anyone actually make the change? Do you have a story?
I think, yeah, like a one-liner would be, it's a carbon-free, inference-friendly, CUDA-friendly solution. Beautiful.
Yeah, I mean, so Vikas, you said the same thing like power, but I mean, JM is here to make money, right? He'll put in power, he gets ROI, he'll put in more power and get more ROI. So at that point, like both of you are making this power argument. Is that convincing to someone like JM or Jensen, is it a big deal?
I mean, it's funny, just looking at, we have B200s in production now, just looking at, they sit at 150 watts idle. Just looking at it, you're like, just as like an engineer, you're like, God, this is so high. Why is it so high?
Why is it so high? Idle. Yeah, that's fair.
So you would buy the pitch from Vikas and Nilesh on the power TCO?
But yeah, the TCO, that's always a, like we have models, to put in the TCO model for how much power things are taking in consumption. The one surprising thing that we've learned about at least AI power, again, this has nothing to do with the storage at all, but the provision power, like of how much with the max power of the spec sheet on these B200s are 14 kilowatts, the B300 we're moving to 16 kilowatts per server. But on average, most of the time they're like sitting there at like 4 to 7 kilowatts. So they're not like consuming 14 all the time, but you have to provision that much power at the data center where you're building it because that you're speccing for this max thing. But again, you'd have to have all the GPUs at 100%, all the CPUs at 100%, all the SSDs at 100%, all 10 NICs that are on that system at 100%. It just never happens. But understanding that, like the reality of what we see and measure versus like what we put on paper, and then how do you design a rack for that? I'm still struggling with how to do that properly, right? It's probably not like, oh, just do the reference design and spec at the max power. I don't think that's a very reasonable thing to do. But at the same time, data center guys are going to yell at you if you, you try to put too much power in the rack. They'll be like, don't do that.
Yeah, and maybe another question, because so you're putting out all these accelerators, but unless NVIDIA puts it in the spec, will anyone buy and what's the pitch to, if you innovate in storage, right, compression or whatever it is you're doing, and there was a question about computation, all this stuff, but unless it's written in a spec, like a system, will anyone actually do something different, and is that a big risk?
So in general, that is true. I mean, today, NVIDIA is such a big gorilla in town that if they recommend, it'll fly, right? But in general, I do believe that NVIDIA, again, looking from outside, they have the right approach in the sense that they're building AI factories and not necessarily just selling GPUs. And they do understand the importance of power. Now, having said so, the queue outside, you can understand NVIDIA is very long. To get their attention is important. But I think that directionally they're right. They're trying to build AI factories, and they're fully cognizant of the power limitation and the memory tiering that we have talked about, et cetera. I think it'll happen eventually. Okay. Right now, they're just consumed making more money out of GPUs, though. So.
Got it. Jim?
Oh, yeah. And then just a final note, because I know we're sort of out of time, but there's a big difference between like inference optimized power, and then like the training and the higher end systems. We're doing the TCO in California, and it makes sense for us, like for super expensive equipment like an HGX or hyperscale, like that's totally fine. When the CapEx is so much higher in the TCO than the OpEx, it's okay. The power is not a big deal. But if you're running an inference optimized card that's like low power, or in the lowered CapEx, for the cards, then yeah, if OpEx suddenly becomes 50% of the TCO, then yeah, if you have a strategy that can reduce OpEx by 50%, that'll be very good. So it's just a matter of what the CapEx and OpEx ratio of the card, not dissimilar from what we have in storage, right? And by the way, the GPU TCO model looks a lot like our SNIA storage TCO model, just with different things on it.
Got it. Any other questions from the audience? I think we have a few more minutes, so I just want to make sure. Any questions? Any other questions from the audience? No more?
Time for lunch.
Oh, yeah, everyone needs lunch. Yeah, Bill, here, let me give you the mic.
Yeah. Any follow-up?
Just to follow up to our previous conversation, Stephen. So with that response about the efficiency of AI versus the efficiency of traditional computing, I guess I read that response as saying that is AI now the dominant processing cycle, and is traditional computing essentially fading or becoming a secondary concern?
I don't think so. I'm waiting for some academic somewhere to come up with like a new transformer model that uses different math to get from input to output like 100 times more efficiently. I find it kind of amusing that we're like building these supercomputers that do a lot of linear algebra, and I'm always terrified that we're actually nowhere near the optimum transform from unstructured data to like a clever AI. And so, the day that happens, it's going to be fun because no silicon is going to be anywhere near as efficient as it can be, and we're all going to be off building things that do tanh functions. GPUs are very good at multiplying things together. That's really what it comes down to, right? And if they weren't, we wouldn't be using them for this particular workload. Are CPUs dead? No, because we need operating systems. And to be honest, AI is a thing, and it will eventually, become level, and then there'll be another thing. Maybe that's quantum, maybe it's something else.
Do you know, Nick, do you have a feel for what the...
By the way, we just got the time's up sign, so,
Yeah.
but thank you all, thanks for the questions, and yeah, thanks to the panel for taking on the questions, yeah. We can follow up offline.